Hello everyone, I'm Yui Washizu. Today I'll about how to offload Linux network on VMs. Unleashing SR-IOV offload on virtual machines. This is today's agenda. I'm going to divide my presentation into 4 parts. First, introduction about overhead of network functions in virtual network and our purpose. Second, our approach and concept. Then, functional and performance verification about checked if operation and performance as expected. Finally, summary of this talk. First, I'll start with introduction of this talk. The virtual networks of VMs and containers by default have various network functions implemented in software, resulting in overhead. Network functions means routing, switching, or encryption, etc. on platforms like OpenStack or Kubernetes. Software implementation causes the occurrence of overhead on emulation layer. What is hardware offloading? Hardware offloading can drastically reduce overhead of software implementation. OpenStack and Kubernetes especially can use SR-IOV for hardware offloading. SR-IOV enables a single PCIe function to present multiple separate PCIe functions. These separated multiple PCIe functions are called virtual functions, VFs. Network offloading on VMs isn't possible, it's available only on physical machine. So, offloading of container network on VMs is not supported, although there is demand of deploying containers to VM for high flexibility. The same is true for nested VMs. Why can't networking on VM be offloaded? Network construction software can't access SR-IOV physical PF. Network construction software Network construction software such as SR-IOV CNI plugin configures networks by accessing SR-IOV PF. Therefore, as shown in left figure, when deploying containers to physical machines, the software can access PF and assign VF to containers. But, as shown in right figure, in the case to deploy containers to VM, the software can't configure network because it can access the PF. We considered 2 ways to solve this problem by existing function. First way is pass-throughing host VF to VM. But this way can't control SR-IOV within guest because it's not possible to use SR-IOV CNI etc. And it's hard to add feature of SwitchDev SR-IOV on guests because the guest can't create web device for SwitchDev mode without accessing to PF within VM. And second way is to assign PFs to VM and to allow VMs to exclusively access PFs. This way lacks scalability and introduces security concern. Because the guests can access to physical PF directly. Next, about our approach. We propose this approach, Virtual PF. This approach is to emulate PFs that have SR-IOV feature. These emulated PFs are called Virtual PF. We implemented mainly in CAM for this. What is possible by Virtual PF? Virtual PFs can be accessed by network construction software in VM as shown in this figure. So, this allows host SR-IOV to be controlled within the guest. This way is SR-IOV emulation. And Virtual PF can handle hardware control requests from the guest through the Virtual PF. Handling control requests means that the guest can create new VFs and configure virtual network. These created VFs are called virtual VFs. SR-IOV emulation has some advantages. First, we can use SR-IOV in same way as the way on physical machine. This means that application works same as on physical machine, so it's available to use existing network construction software such as SR-IOV CNI, SR-IOV CNI plugin, etc. And by this, the guest can create web device for switch-dev mode in the future. Second advantage is that this way has scalability and less security concern. It's because the guest doesn't directly access the PFs. Scalability is kept by needless to assign one PF per VM. And guests can't control entire NIC hardware, make security concern less. But it's not possible to accelerate network by SR-IOV emulation. So we use virtual I/O data acceleration VDP device for backend. These figures show the network acceleration by VDPA. VDPA can offload only data plane without offloading control plane. So, by using CAM with feature of Virtual PF, the guest can directly access physical VF in control plane, but the guest can access physical VF in data plane. This way can be accelerate network because the guest doesn't have to access emulation layer in data plane. And this way is useful for purpose other than acceleration. By replacing backend, this way can be used for other use cases because the backend is pluggable. For example, this even utilizes tap devices to test SR-IOV for guest OS. Such as these figures, it's possible to select the kind of devices as backend. When we want to accelerate virtual network, the backends are VDP devices, or when testing and debugging for guest OS, top device also is used as backend. Next, we have FutureWorks SwitchDev SR-IOV in guest. We have potential solution for guest SwitchDev mode with OBS. We considered CAM and libvirt etc. handle TC configuration from the guests. When getting TC command from guest, CAM or libvirt send OBS it as OBS OF control OFCTL and command. Then host OBS controls offloading and bridge in OBS might be for offloading guest switch. Next, I'll talk about functional and performance verification. The purpose of this verification is to confirm performance improved by VDPA and SR-IOV CNI plugins correct working. This table shows verification targets set up. Server model with HPE ProLiant DL360 Gen 9 and CPU with Intel Xenon CPU and NIC was Connect 6 DX 100 gigabit NIC. Host and guest OS were Rocky Linux 9.2. CAM version was 8.1.1. This CAM is with virt.ionet legacy SR-IOV support POC patch applied. Kubernetes version was 1.27.6. 1.27.6 and CNI plugin we used was Calico version 3.26.3 and we used SR-IOV CNI plugin 2.7 with slight modification caused by current virt.io limitation. Structure of virt.io sysfs is different from other common devices because virt.io bus is under virt.io PCI device. These figures show target environments. We used legacy SR-IOV BFs as backend and netproof as measurement tool in both two environments. Left figure is comparison target without offload in VM. This uses Kubernetes network, including firewall and net through software. Right figures is the environment applied our approach, Virtual PF. Hardware offload is used on guest by SR-IOV CNI in this. This shows verification metrics and section. We measured between application on guest container and application on external machine, such as green arrow. Then, I'll explain the improvement of throughput and latency. First, this is about throughput. The value of the measuring result means the average throughput of UDP bulk transfer using Netdev. These graphs show the result of transmission and reception. Transmission performance in the target with offload in VM with about 1.2 times as large as one without offload in VM. And reception was 6 times better than without offload in VM. Next, and this is about the latency. The value as the measuring result means the 99 percentile of round-trip time of UDP request and response using Netdev. These graphs show the result of latency. The performance of latency with offload in VM is 100 microseconds less than one without offload in VM. Finally, a summary of this talk. The background of our attempt is that there are cases to deploy containers to VMs for high flexibility. So we aim to achieve offloading Linux network on VM to SR-IOV physical NICs. Then, and we proposed method, VirtualPF. This way make application work same as on physical machine using SR-IOV emulation, and enable to offload NIC containers virtual network using BDPA. The improvement by this approach is throughput transmission performance became 1.2 times better and reception performance became 6 times better, and the latency was 100 microseconds less. So we could confirm the effectiveness of this approach. Thank you. Thank you for listening.
So when you ran your benchmarks, how much load was on the CPU?
Okay. And it's single core, eh?
But like, was the core itself loaded? Because one of the big benefits of SR-IOV is that because you're not creating a virtual NIC and switch, the CPU is not being loaded. So if you had like a CPU that's pegged near 100%, and you switch from being fully virtual to SR-IOV, I would expect to see the benefits be even greater.
More slowly, please.
So the benefit, from my understanding of SR-IOV, is that what you were doing in software on the CPU, which is emulating the NIC and the switch on the CPU, you no longer have to do that. And where you really see the benefits in the workloads is that when you have a high compute system, you no longer have to do as much networking on the CPU. And so I would expect that if the system was fully loaded doing something computationally intensive, that you'd actually see even greater benefits. And so what I'm asking is, did you test under load besides networking doing something computationally intensive to see how the effects are there?
Okay.
Over here, okay. Maybe one way to say this is if the throughput improved, it's because you saved some CPU cycles.
Yeah.
Right?
More than it did. because it was only like a 6x improvement, something like that. And for virtualization, it's usually much more intensive.
My guess is because you use UDP, and the segments are MTU sized. But if you had done TCP, you'd probably have seen much better numbers. Right? Anyway, that
over here, if I may. I would like to recommend a test to your team. It's called the Flint Rule Test, RRUL. It tests downloads, uploads, and late UDP latency at the same time, and it is the best way to determine that if your offload is working well or not.
Sorry, Adam, repeat more, please. Sorry.
Flint is the name of the tool, FLENT. The test that I love people to try in this kind of scenario is the RRUL test.
RRU test.
RRUL, 2 R's. Thanks.
you can talk to after. Is there anybody online with a question? Okay, there's nobody online. Okay, thank you, Yui. Oh, there's a question.
I was just wondering if you have any documentation or any publications with regards to your work on the virtual PF-VF flows, if people want to try it in QEMU or anything like that.
Are you writing a paper for this?
I'm not yet. Yeah.
Okay, I think it'd be a good idea if you write a paper and make your patches available. So I think the trick you used is you have somehow simulated a PF inside the VM using QEMU, and then you have a virtual VF. Okay, is it two VVF, which is inside the QEMU that you then shunt into the container, right? Okay, that's what she's doing basically. Yeah, write a paper, please. Yeah, thank you. All right. Let's do a hand of applause. Thank you.
Yeah, thank you.